I guess you are able to see my screen.
Yes, sir. Okay.
And I hope I'm audible to the audience also. So, hi everybody, good afternoon. So, this is my second talk, and this is regarding seismic hazard estimation. So, in the morning when we were discussing, there were some questions regarding how to get the time histories or which time history I should use to design for. And before that, even which response spectrum I should use to design for. The response spectrum given in the code, what is the basis of that, how to use it. These questions we will take up in this talk. So when we record earthquake, we can use either an accelegraph, and the recorder of that accelegraph is accelerogram. So the first record which you see here, this is an accelerogram. Okay, so this is record of acceleration, and it is very useful to us because earthquake is causing an inertia force, and inertia force is mass into acceleration. So if we multiply mass by the acceleration, we will get the force applied on the structure. So here you see one peculiar characteristic of earthquake which makes it different from all other types of loading, that it is crossing the zero line. So it is reversing its direction in a fraction of a second. This total duration is roughly 30 seconds. So this is El Centro earthquake recorded for 30 seconds. And what you see that within a second, it is changing its direction several times. So this is a very important characteristic of earthquake, which we make use. And by virtue of this characteristic, we are able to design our structures for much lower earthquake force than what will be experienced by an elastic structure. And as a result, our structure may yield, it may undergo damage, but it does not collapse because earthquake is reversing its direction very frequently. Now, this type of reversal is not seen in other loading. The closest loading to earthquake loading is wind loading, where also you will see the fluctuations. So if you see the wind record, it will look something similar to this acceleration record, but it is fluctuating about a mean value. It is not changing its direction. So we can't take advantage of that, and that's why we take advantage of ductile energy dissipation only in case of earthquake, and that makes earthquake resistant design so special and a little bit complex, because we have to take into account the nonlinear behavior under cyclic loading. Now, another type of instrument which we use in earthquake recording is seismograph. And record of seismograph is called seismogram, and this is record of velocity. So the ground velocity at that location, if we plot, we will get a seismogram. So accelerogram is plot of acceleration, ground acceleration, and the peak value here, whatever is the maximum value we are recording, that we call peak ground acceleration. So this peak ground acceleration is one measure of intensity of ground shaking, and this we can obtain from accelerogram. Then peak ground velocity similarly, which is obtained from the record of seismograph, and that peak value is also important. So another intensity measure is in terms of peak ground velocity, or PGV, and we can integrate the velocity plot, we can get the displacement plot. There is no method by which we can record the displacement directly. So far that instrument is not there, and whatever attempts are being made to record the displacement, those are being made through satellites. So maybe in future we will get the displacement record of an earthquake also sometime, but currently the displacement is obtained either by double integration of acceleration or by simple single integration of velocity. And from here we get another important measure, that is PGT, peak ground displacement. So these are the intensity measures, and these are the typical earthquake records. Now, if we look at the earthquake records of past earthquakes, which have been known for quite damaging earthquake, we can see that these are quite different. Their seismograms or accelerograms, here I have accelerograms, are very different. So these are like unique signatures of those earthquakes, and each earthquake has its unique signature. So whatever earthquake is going to come to my site, one thing is sure, that it will be different than all earthquakes which have been recorded so far. So it is going to be different. It is not going to match with any of those earthquakes which have been recorded in the past. So one question which we have to answer is that which earthquake I should use in our analysis. And the first thing which comes to our mind is that one single earthquake is not going to be enough, because the earthquake which we will record or which will affect my site or my structure will be different than the past earthquake. So we have to at least consider a number of earthquakes. And then we have to identify some salient characteristics. We have to decipher these accelegrams to understand the hidden information in that. So we have to look at their characteristics. So if you look at the characteristics, these plots here, what you see that in some of the earthquakes, the amplitude is very large. And all these earthquakes are damaging earthquakes. So the first earthquake is damaging. It is a small duration earthquake, but because the PGA is very high, so naturally the high PGA will result in high force, and due to that force, the structure gets damaged. Then this earthquake, it or let's see first the Chile earthquake, then we'll come back to the Loma Prieta earthquake. So if you look at the Chile earthquake, so Chile earthquake, there is medium amplitude, but that amplitude is continued for long duration. So the duration of shaking is very large. Now, in case of earthquake, this duration of shaking is also important. So it is like every pulse of earthquake, when it comes, it causes some tiny uh, damage to my structure. In fact, in case of earthquake, it is not tiny. If we are talking about fatigue, where the surface load is causing this type of fluctuations in the stresses, that is also causing some damage in each cycle. And if the damage gets accumulated for millions of cycles due to fatigue, we get the failure. In case of earthquake, we call what we uh, get is the low cycle fatigue. So with limited number of cycles, it is not millions of cycles, but limited number of cycles, because the deformations are in elastic range. So the structure get damaged or collapses with fewer cycles, and each cycle is causing the damage, so damage gets accumulated. So the duration of earthquake is also very important. So far, whatever analysis we have talked in the morning, we have seen that we have not talked about duration, because duration will come into picture only when we are performing a nonlinear time history analysis. Then only we can take effect of the duration. So in linear analysis, we can't take into account the effect of the duration. So duration is considered an average duration. But if you look at this Mexico City earthquake, this is very peculiar. I will talk about this earthquake later again. But what you see here, the amplitude is very small as compared to these earthquakes, because it is plotted on the same scale. So you can see that the amplitude is very small, just a small fraction of these. But still, this earthquake caused a lot of devastation in Mexico City in 1985. And in fact, this earthquake was so peculiar that whole branch of soil structure interaction, dynamic soil structure interaction, started after this earthquake. So there was a lot of focus on the effect of the soil. So because of the effect of the soil, the characteristics of this earthquake are such that it is taking a lot of time in reversing its direction, or we can say that its frequency of or the frequency predominant frequency band is in quite low frequency range, and unfortunately that frequency matches with the frequency of most of our buildings between 5 to 20 story. And as a result, in Mexico City during 1985 earthquake, there was a selective damage between 5 to 20 story buildings. Those buildings were very badly damaged, and the shorter and taller buildings were spared, because this had a resonance, quasi-resonance like situation. In case of earthquake, resonance is not possible because frequency is not same. It is not a harmonic type of loading. So resonance does not happen, but a quasi-resonance like situation happens when the period of vibration of the structure and the predominant period of earthquake motion are close, and then the response of the structure increases. So we can identify that there are three important characteristics of an earthquake motion. One is the magnitude. So the magnitude, sorry, before characteristics, there are two commonly reported aspects of an earthquake. One is the magnitude and another is the intensity. So magnitude is indicator of the total energy which is released during the earthquake rupture. And the most popular scale, there are several scales. The most popular scale which we hear on TV is Richter scale. But this is of magnitude. Now magnitude you can relate, like if I take an analogy with an electric bulb. So magnitude is like wattage of the bulb. Larger the wattage, okay, more energy it can emit. So total amount of energy which is emitted by the earthquake, that is magnitude. So magnitude is like the wattage, but it is not important to us if that large magnitude earthquake is occurring far away from our site. So the distance of this magnitude is also important. So intensity is of importance to us, and in intensity, what we do, what intensity is indicating? Intensity is indicating the severity of ground shaking at any site. So it is like the light intensity available at a site which is required to read a book. So if I go away from the bulb, the intensity, whatever is the wattage of that bulb, away from the bulb, I'm not going to get sufficient intensity. So similarly, if away from even a large magnitude earthquake, if we are far away from there, then the shaking level will be so low. So before instruments were available, people were quantifying this intensity by some subjective scales like MMI and MSK, instrumented intensity scale now we are having, because we can now measure PGA, PGV, and whole response spectrum. We can get the ground motion itself. We can get through instrumentation. And then we represent it through accelerogram and seismograms as obtained from these instruments. So coming back to that question, that which earthquake I will use, so I need to identify the characteristics of those acceleograms. So there are three characteristics of the acceleograms which define its damage potential or level of shaking, which we need to consider. One is the amplitude of shaking. So PGA, PGV, and PGD, these are the three peak amplitudes. So these are important to us. So larger PGA means more damage or higher intensity. But the PGA alone is not enough to define the intensity of shaking. It will also depend on the frequency content. So if the frequency content of that ground motion is in the range in which our structural frequency of vibration is there, then the damage is going to be much more. But the frequency content of the earthquake is very different than our structure, then this damage is going to be less. Unfortunately, for most of the cases, the predominant frequency of the earthquake, then the frequency of vibration of the soil on which our structure is located, and the frequencies of the structure are close. Even if those are not coinciding, those are close. And that's why this becomes very important. And then the duration of the earthquake, as I said, that longer duration earthquake will cause more damage because the damage is accumulated, and this we can take into account only in case of nonlinear time history analysis. So duration we can't take into account in our linear analysis. In linear analysis, we take into account amplitude and frequency, and these two parameters are taken into account in response spectrum. So response spectrum is representative of the amplitude of the ground motion as well as its frequency content. And how we obtain response spectrum? We take a series of single degree freedom systems. So these single degree freedom systems are having increasing period but same damping. So damping is kept same, let us say 5%. Most of our response spectra are plotted for 5%, but we can have any other damping also. So damping is constant, but the period is increasing. So you can see this is a shorter and less mass single degree freedom system. This single degree freedom system is having larger mass and it is taller. So this taller will vibrate slowly and the shorter will vibrate rapidly. So the period is increasing. So same ground motion, if we put at the base of all these single degree freedom systems, so I will get the responses. And these responses are going to vary with the period. So different single degree freedom systems will have different responses, and the response will depend upon the period of that single degree freedom system and damping. And damping is constant, so it will depend on period. And if I take the peak response of this, then plot that peak response. So response can be any quantity. Response can be acceleration of this single degree freedom system. It can be displacement of the single degree freedom system, it can be velocity of the single degree freedom system, and sometimes it can be even moment or shear force or stress or strain. Any of these response quantities I can take, and if I plot those response quantities with period, so I will get a graph, and this graph we call response spectrum. If I have done it for acceleration, then we call it spectral acceleration. So this is representing, this response spectrum is representing the peak response of a series of single degree freedom systems which are having increasing periods. And this plot is very important to us. Some of you may be already familiar with the importance of this, because if response spectrum is available to us at any site, I can read the peak response of single degree freedom system from this response spectrum, as we have seen in the first talk. Now, two extreme conditions of these periods we can see. In one extreme condition, I have put just a rock block or a block of concrete inside the ground. So this is representing a very rigid structure. So very rigid structure means its stiffness is infinite and the period is zero. So it will not be possible to make the period exactly zero. But if I make it quite rigid, more, let us say its frequency is more than 33 hertz, or the period is less than 1 by 33 second. So that we can consider as rigid. And what will happen when the ground is shaking? It is embedded into the ground. So when ground is shaking, its acceleration will be same as that of the ground. So at very high frequency or zero period, we get the acceleration of the structure same as that of the ground. That is one extreme of this response spectrum. So if I take this right up to zero period, so this line corresponds to zero period. So when if I take it here, it will intersect somewhere here, and this value will be representing the ground acceleration. So it is not ground acceleration exactly. There is some sort of averaging, because ground acceleration can vary a little from point to point. So this is doing an average. So it is sort of an average peak ground acceleration, which we call effective peak ground acceleration EPGA, or zero period acceleration ZP. And what is given in the code as the zone factor is actually this only. So that is, the zone factor is representing effective peak ground acceleration, or EPGA. It is close to PGA, it depends on PGA, but it is not PGA. It is the value of response spectrum at zero period. We will talk about this in more detail. And then the other extreme is that there is a very flexible structure, like a balloon in which is connected by a thread. So if it is a very flexible structure and I shake the ground, what will happen? This mass will try to remain in its position, whereas the flexible support system is going to move. So here we can see that the displacement, the relative displacement of the mass and the ground will be same as the displacement of the ground itself, because this flexible system is not moving from its place. So in case of a very flexible system, the acceleration will be zero. This mass is not going to have any acceleration. So acceleration will tend to be zero, and the relative displacement will be same as that of the ground displacement. So relative displacement will be equal to the ground displacement. And our real structures will be in between this. So these are the two extremes. And real structures will vary. Those can be very rigid. For example, if I'm having a single story building, the period may be 0.1. If I'm having a, let us say, gravity dam, the period may be very small. And if I'm having a tall building or a tall chimney or a tall bridge, in this case, so we are going to have a very long period. So our structures will be somewhere in between these two extreme conditions. So for a typical earthquake, let us say L-shaped earthquake, for which I have shown you the accelerogram, if I plot the response spectrum, which is representing the period, the response or acceleration at different periods. So here it is plotted for displacement. So displacement spectrum will be something like this. It will go on increasing with period, and then it will tend to become constant. So this is the typical shape of displacement spectrum for one earthquake. Then I can plot the velocity spectrum in the same way. Velocity spectrum means peak velocity of that series of single degree freedom systems, which we have discussed. It will increase then it will become more or less constant, and then it will decrease again. Now, if we look at the acceleration spectrum, so acceleration spectrum is something like this, where it increases initially, then it becomes constant, and then it is decreasing. And you see there is a flat portion here. A small flat portion is shown here. So this flat portion is representing that short, very short period, 0 to 1 by 33 second, or 0 to 0.03 second. So up to 0.03 second, the response is constant, and it is same as that of the zero, at the zero period, or what we call EPGA. So it is similar to EPGA, rather it is EPGA or ZPA, and it is given in our code as the zone factor. Now, effect of the local soil is very important, and the frequency content in any ground motion will depend upon the soil below the foundation, because the seismic waves will travel in the bedrock, then from bedrock these will travel through the soil layers, and then these will reach to the structure. So depending on what type of conditions, ground conditions we have at the site, the shape of the response spectrum is going to change. For example, here A, this is representing the shape of the response spectrum under a rock site. So if the site consists of rock, firm rock, then the low period or high frequency contents will be more in the ground motion, and the peak response I'm going to get corresponding to low frequency. But if it is a alluvium soil where soft soil layers are there, then the peak will shift. The peak is going to occur corresponding to a period which is the period of vibration of the soil. And we can see here, this is also coinciding with the periods of different stories. So for example, this 0.5 second, or this is 0.3 seconds where we are getting this peak. So that will correspond to 3 stories. And this peak, it is somewhere between 10 to 15 stories. Roughly the period of the building you can take as 0.1 n. However, such simple formula is not available for bridges, but the bridges, most of the bridges will also be in the same frequency range. So the bridges will also get affected similarly depending upon the soil conditions. So if there are soft soil conditions, those will cause more damage in taller buildings or taller bridges, flexible bridges. If the soil conditions are rock, the site is rocky, then the frequency content is going to match with the shorter structures, and the shorter rigid structures will be subjected to more damage. Then I talked about this Mexico City earthquake. It is very interesting study. So in 1985, an earthquake came, and then again recently in 2000, around 2010 or after 2010, another earthquake has come. Both have very similar characteristics. I have taken this from 1985 earthquake. So Mexico City is located on the dry bed of Mexico Lake. So there is a Mexico Lake, and it is Mexico City is located there, and the depth of the deposits at the rock, at the bottom of the lake are increasing towards the lake, as it is obvious. So near the city we have the foothills, and then the depth of the bedrock goes on increasing. So two recording stations were there in 1985. One is this UNAM, University of Mexico, and another one was a station located here, SCT. So UNAM was located on rock, on the foothills. So where rock is available at the surface. So we can see that here there is no effect of the soil. Whatever we are getting is the vibration of the rock itself. Here, the depth of the soil deposits is roughly 30 meters. So this 30-meter deep soil deposit is there, and the records of these two are shown here. Whereas in UNAM, the record was this. It got amplified at SCT, but still we can see amplification is not that much. It is not so alarming. So this amplification took place because of the soil layers. But very importantly, the most important effect we saw on the response spectrum. So if you look at the response spectrum of the motion recorded at UNEM, so this is the response spectrum. But the response spectrum which was recorded at SCT, there was an amplification corresponding to 2 seconds. And this 2 seconds, we can do a simple calculation for the period of the soil column of 30 meter. So here it is done for 37.5 meter. So it comes out to be exactly 2 seconds. So corresponding to 2 seconds, we got the peak. And here, although the PGA was small, PGA was not that large, the spectral acceleration, because of the focusing of the energy into this frequency band due to the filtering action in the soil. So all the energy was transmitted in this frequency range, and the other frequencies were stopped by the soil. So we got energy focused here in a particular range. It got intensified, and here we can see that the assay is quite large, 0.8 G. So from 0.1 G, it increased to 0.8 G, 8 times increase due to this soil amplification was seen. So this local soil condition can create a lot of difference. So currently our code takes these into account only on average, but in certain soil conditions, especially when we have deep alluvial soil and the intensity of shaking is low. So if the intensity of shaking is high, then this type of amplification or this much amplification is not seen. Amplification is there also, but this much amplification is not seen. Amplification reduces significantly because the soil has two actions. One action is that it is filtering the frequencies which are matching with the frequency of the soil column, and the energy in those frequency range gets intensified. The second thing it is doing, it is causing dissipation of that energy. So when waves are propagating through the soil, due to its nonlinear static behavior, the soil is dissipating energy. So in case of high amplitude motions, the energy dissipation is large, and due to that the amplification reduces. But in case of low amplification, low amplitude motion, the amplification is very large because so much dissipation does not take place. In a way, that is good also, because if you are having 8 times amplification in case of high amplitude motion, it would have been impossible to design. It would have been too much. So we get this type of amplification for low amplitude. So we have to be very careful in on the sites which are in zone 2 or zone 3 and where deep alluviums are there. So there we can get very high amplification of the ground motion, much more than what we have estimated. And that's what Mexico earthquake has taught us. So keeping that in mind, our code, or for that matter, all the codes of the world, they provide a smoothened response spectrum. So I told you that for one earthquake, this response spectrum is quite zigzag. It is jagged. But if you consider a large number of earthquakes and normalize those with the corresponding EPGA or PGA, or ZPA. So EPGA and ZPA, that was the value at 0 period. So if you normalize by that, this value will become 1. But this will be the shape. It is not response spectrum, but it is a spectral shape. So what is given in the code is actually spectral shape. If you multiply it by the corresponding ZPA or zone factor, then it will become response spectrum. And then 3 spectral shapes are given. One for rock, another one for medium soil, and third one is for the soft soil. And the amplification in this is 1.67. So 67% increase has been considered in the long period. So here we don't see any specific peak in the long period, but we see that the whole of the response spectrum has been increased, because the period at which that peak is going to occur will depend upon the local site. It will vary from site to site. So this response spectrum tries to take into account in an average sense. But if we are expecting large soil amplification to occur, we should perform a site-specific analysis for amplification. Another interesting thing you notice here, that in this range, the response spectrum is constant. Acceleration response spectrum is constant. Then it is decreasing proportional to 1 upon t. So this range we call acceleration control range. This range up to 4 seconds as velocity control range, and beyond 4 seconds it is constant. So this constant is not a right assumption. This can create problems. So I will just discuss. So in a real response spectrum. This initial flat range, we call it acceleration control range. This range we call velocity control range. And in fact, there is a range beyond a long period, corner period, what we call TL. It is proportional to 1 upon T square. This is called displacement control range. And in AC7 as well as in Eurocode, this type of response spectra are given. In Eurocode also, there is a period TD beyond which it is displacement controlled. It is proportional to 1 upon T square. So this acceleration response spectrum, we can convert into displacement response spectrum because this is response of a single degree freedom system. So we can just take SD as SA T square by 4 pi square, and then if I multiply this by T square by 4 pi square, the initial increasing portion will become a cubic parabola. Then we will have a parabola, and then this 1 upon T, this will become linear. So it will go on increasing linearly till the velocity control range ends 4 seconds. Now what will happen after that? After that, our code has assumed the response spectrum to be constant, and when I multiply it by T square, it becomes parabolic. So in our code, if I convert the response spectrum given in our code to the displacement spectrum, then beyond the 4 second, the displacement is going to increase parabolically, very high increase. Whereas in reality, after this, it is displacement control range. So it should be proportional to 1 upon T square, and the displacement should become constant. So at longer periods, this displacement should have been constant, but currently our code, if we follow the response spectrum of our code, it will indicate that the displacement is increasing tremendously in a parabolic fashion. So that array is not there in IRS because IRS considers the old response spectrum up to 4 seconds, and beyond 4 seconds it has been assumed to be constant. And then the effect of damping also we can take into account. So normally we are plotting this response spectrum for 5% damping. Damping may be less than 5% also. So for 2% damping and 5% damping, it increases. So as the damping reduces, the response increases, and hence the response spectrum. And as the damping increases, the response goes on decreasing. So at any period, if I know the damping, then also I can get the response from these plots. Response spectra plot for different damping. Now that error which I was telling, that beyond 4 seconds, if our code assumes constant, that has been done away with the recent revision which is undergoing. So this IS 1893 2023, but this is probable 2023. So it is currently under wide circulation. So comments from people are being invited, and after that it will be finalized and submitted. That means it is quite in advanced stage, and there you can see that the shape of the response spectrum is given like this. It is assumed constant up to 0.01. So earlier I told you that up to 0.03 second it should be constant, but here it has been assumed to be constant up to 0.01. Then it is increasing acceleration, then acceleration plateau, and then it is proportional to 1 upon T, and then it is proportional to 1 upon T square. So we have constant acceleration, we have constant velocity, we have constant displacement ranges. And our constant displacement range is assumed to start at 6 seconds. Eurocode, it is just 2.5 seconds. In American code, it varies from place to place between 6 seconds to 12 seconds. And the period beyond which the velocity control range starts, you can see that these periods have also been slightly modified. It is now 0.4 second, 0.6 second, and 0.8 second. Okay, the shapes have been slightly changed in the revised. More than the shapes, the zone factors have been changed. I will talk about that in more detail. So spectral shape is given in the code, but still we need the zone factor. If I have to use the shape given in the response spectrum given in the code, I need a zone factor or ZPA, zero period acceleration, or EPGA, effective free ground acceleration, so that I can multiply it by the shape given in the code, and I will get the complete response spectrum. So there are two methods to obtain the response spectrum or the PGA, and in general, it is called seismic hazard assessment. So any parameter related to seismic intensity we can obtain using these methods. So as the name suggests, in deterministic seismic hazard assessment, we give a deterministic value that the zone factor for this site is this much. There is no probability associated with it. So it is in a way the maximum earthquake which we are expecting at a site. Currently, our code is based on DSH. The code which is in circulation, that is based on PSH. So that is the major difference between the IS 1893 2016 version, and same was there in 1984 version also. So that was based on DSHA. This is based on PSHA. So a study, probabilistic seismic hazard assessment study, has been conducted for all of the country, and based on that, a PSHA map, hazard map, has been prepared. In probabilistic seismic hazard assessment, as we understand, it provides, in addition to the amplitude of shaking or the response, it also provides the probability of accidents. So it considers all the uncertainties and the variabilities which are there in the data, using which we perform the seismic hazard assessment, and then convert that into probability of accidents in a particular time. So generally, this time is taken as 50 years. That is the design life of a structure, and this is the additional information we get as compared to DSH. So the hazard is classified based on either the probability of accidents or the corresponding return period. These are related. The probability of accidents in a given period can be related with the mean return period, and the most commonly used, the three most commonly used labels are: one is this SE, serviceability earthquake. So serviceability earthquake corresponds to 50% probability of accidents in 50 years. So it has a return period of 72 years. So this is an earthquake. It has 50% probability of occurrence. So 50-50 chances it has. So that means that such an earthquake is likely to be expected during the service life of a bridge or a structure. So that means we have to design our structures to remain serviceable. If such an earthquake is going to visit, then our structure should be serviceable. That's why we call it serviceability earthquake. Then another one which we commonly use in our design is this 10% probability in 50 years, 475 years. We call it design basis earthquake. And this level of earthquake is used for designing the structures. Now, it is somewhat paradoxical that we design our structure for DVE, but we want our structure not to collapse under MC. So what is this MC? MC is sort of maximum possible earthquake at a site, and in probabilistic terms, it is 2%, only 2% probability of accidents in 50 years, and the corresponding return period is roughly 2,500 years, 2475 years to be more precise. So 2,500 years return period, and this earthquake we consider as the testing earthquake, the big one. And our structures should be able to survive this earthquake without collapse. Although those structures may be damaged, those may not be serviceable. In case of bridges, we will see what are the requirements. In case of buildings, normal buildings, ordinary buildings, when we are designing, then we are only expecting that under earthquake, it should not collapse. Now in ASTO, there is another earthquake used with 70% probability of accidents in 75 years. So they are not using DVE, 475 years return period, which is used in our code. They are using 1,000 years return period. And if you compare this into 50 years, because here bridge life is considered as 75 years, building life is considered as 50 years. So if it converts into equivalent, then the 7% in 75 years is same as roughly 5% in 50 years. So 5% chances in 50 years, roughly 7.5% in 75 years, or 7% we can say in 75 years. So what is used in ASTO in design is this 5% in 50 years in place of 10% in 50 years, what is given in our code. So Astro is designing the bridges for higher uh, return periods or higher intensity of shaking as compared to our code. Now you may be familiar with this current zoning map. So in current zoning map, the whole country is divided into 4 zones, starting from zone 2 to zone 5, and the maximum value of JAD is given as 0.36. So this JAD is fed as a factor, but actually what it is representing, it is representing the value of EPGA or ZPA, zero period acceleration, in terms of G. So 0.36 G is the mean value of zero period acceleration, which is obtained from DSH, because currently the code is based on DSH. So using DSH, this value of 0.36 G in zone 5 has been obtained. So we have to keep in mind that this is what is obtained from DSH. It is not MCE, it is not DVE, so this 0.36 G is nothing DVE or MCE, because it is based on DSH, and the concept of DB and MC is related to PSH. So it is not a PSH map, it is a DSH map, and there we have the values as mean, 84 percentile or 16 percentile or any percentile, mean plus some value of sigma we can take. So these are the mean values, 0.360. So we have been using, our designers have been using this terms of MCE and DVE in Indian design also. Although our code does not talk about DVE or MCE, but the designers have started using these terms DVE and MCE, and that has caused a lot of confusion that this zone factor JAD, which is given in our code, whether it is DVE or MCE or something else. So if we look at ASC 7 2006 version, recent version, then the definition of deterministic MC ground motion is given as the 84 percentile damped 5% damped response spectrum is considered as MCE. So MCE considered to 84%, whereas what is given in our code is mean. So it is not MCE. And if we look at the older versions of ASC7, 2005 and older, after 2005 they changed the definition to 84 percentile. Before that, they were using a definition of 150% of the largest median 5% damped response spectrum. So median response spectrum into 1.5, that can be considered MC. So if we multiply our JED with 1.5, then it will be considered as MC. And that factor is already there in our code. And that factor is in terms of the partial load factor we have in case of earthquake. So there is a lot of confusion in our code because of that partial factor. So some people think that this is load factor over and above the MC earthquake, but it is not so. So we have to understand that in our code, current code, the zone factor JAD, which is given, is median EPGA, which is also known as zero period acceleration, ZPA. It is obtained from DSH. And 1.5 into Z can be considered as 84 percentile, equivalent to 84 percentile. If we compare the ASC document older and the new older document, it is 1.5 times mean or average or median, or and in case of new code, it is 84 percentile. So 84 percentile, or when we multiply it by 1.5, so 1.5 Z can be considered as MC, and 1.5 Z by 2. So this by 2 is to convert the MC to DV. So from 475 years to 475 years return period, this ratio is considered as 2. Although this ratio is also not constant, it varies from place to place. And some studies have shown that within the US, it is varying from 1.5 to 2. So I'm not sure about its history, but it looks like that in old American code, this factor was taken at 2. We have taken from that 2, and we are considering that because no probabilistic study has been done so far which establishes this factor, that whether it should be 2 or something else. So this factor 2 is to convert from MCE to DV. So 1.5 into Z by 2 or 0.75 into Z, that can be considered as the DV level earthquake, and this dB level earthquake is used in design, ULS or limit state design. This is used, and this is currently being used. So this is consistent with our code, because our code considers Z by 2 in calculation of AH, and then it considers a factor of 1.5 in the load factor as a load factor. So that's how it converts the median value obtained from DSHA into dB. And if I do not multiply by this 1.5, I use only Z by 2, then this is representing serviceability earthquake. Serviceability earthquake is to be used in working stress design or satisfying serviceability limit states in the code. So for serviceability limit states, we are using Z by 2. So our code is consistent, but it is not clear, it is not clearly defined that what is dBE or MCE. That is not clearly defined in our code. But actually it is using dBE through that load factor, and it is using SE for working stress design. Now this can be further validated if we consider the load factors in different modes. So to represent what we have seen in the previous slide graphically, so this value here, this is the shape given in our current response, current code. This is the shape of the response spectra for 3 types of soil, and this value here is given as 1. So, and this is given as SAYG. So it is wrong. This cannot be SAYG value. SAYG cannot be 1. Actually, it is SA by Z, because it has been normalized by the zone factor or 0 period acceleration or peak ground acceleration. So actually it is representing SA by Z, and that's why we have to multiply it by Z. And when I multiply it by 1.5 Z, then this becomes response spectrum corresponding to MCE. And if I multiply it by Z, 1.5 Z by 2, then it becomes dB. And if I multiply this by 0.5 Z alone, then it is serviceability earthquake. So when we are calculating the earthquake forces using Z by 2 into I by R into SA by G, actually we are getting the forces corresponding to the serviceability earthquake, which is to be used directly in working stress method or in serviceability limit state. And when I'm using 0.75 into Z, then it becomes dB. And if I am interested for MC level response spectrum due to some region, maybe in performance-based design or somewhere, I may need this MC level response spectrum, then I could multiply this by 1.5 times Z. Then we can have a look at the load combinations in ASC7. So in ASC7, the load factor for earthquake load, this EV is the vertical earthquake and EH is the horizontal earthquake. So you can see that the load factors are 1 for limit state design. Whereas in case of allowable stress design or working stress design, you can see this factor is 0.7. And if you look at the ratio of these two, the ratio comes out to be 1 over 1.5. So ULS forces are 1.5 times higher than the SLS forces. Okay, so that factor of 1.5, which is given in our code as load factor, that is representing this. Similarly, if we look at ASTO is also giving the load factor for earthquake load as 1. But in our code, we know that the factor for earthquake, okay, current code is 1.5, and this has been done away because in the draft under circulation, this is based on PSHA, and there the response spectra are defined directly for dB and MC. So there this load factor has been done, and you can see here also the earthquake load factors are 1. So this is in IS 1893 2023, which I have written possibly. It has not yet been published, so I'm just expecting that it will come in 2023. It is currently in wide circulation. So here you can see that the earthquake load factor is 1, but the earthquake load factor in working stress method, you can see okay, so here it is defined directly. So in working stress, we will see later. So working stress level earthquake is defined there. So you can see that this is EED and this is EES. So earthquake force for design and earthquake force for serviceability limit states. So the periods of these two earthquakes are different. So period for these earthquakes for normal building is less than 475 years, whereas here this is 475. And which earthquake we will use for serviceability check and strength check, those are also given in the earthquake. So for normal buildings, normal structures, we have to use 475 years for strength check and 73 years for serviceability check. So EES in the previous slide. So this EES here, this actually corresponds to 73 years. In case of important structures, important buildings, this can go for, this is for 975 years. And bridges, important bridges are also coming in this category, bridges of set 2. So those are also to be designed for 975 years. So you can see that now it will become at par with the ASTO. ASTO code also is designing for 975 years. Our code is also suggesting for 975 years. And the serviceability earthquake here will correspond to 225 years period. And even more important buildings, critical buildings, those are to be designed for a return period of 2475 years and serviceability check at 475 years. So important buildings, lifeline buildings and dams, those will be designed. Bridges of set 3, very important bridges, those will be designed for MCE. Although this is still a proposal from BIS, it is yet to be adopted by RDSO and IRC. So I'm not sure how they are going to react it and whether they will accept this or they will come out with some other return periods. But what this draft code in wide circulation is suggesting is that the very important bridges, those should be designed for 2475 or 2500 years return period or MC. So this should be designed for MC and serviceable for DB. Whereas important structures, those will be designed for 975 years. And normal structures will be continued to be designed in the same manner for DBE and to be checked for SE, 73 years or 75 years return period earthquake. So this is a proposal in the code under revision. And in the new code, which is under revision, there are now 5 zones, zone 2 to zone 6. And the 6th zone is this. So a new zone has been created here. You can see whole of the Himalayan range to northeast is coming in this. So this is having the maximum hazard, and the Bhuj area in the Gujarat, which is already known. This was there earlier in zone 5. So out of zone 5 and 4, 2 zones 5 and 6 have been created. 6 is the most now the most hazardous zone, and then zone 5 is the Indo-Gangetic plains, okay, and then we have this zone 4 in Delhi. So you can see Delhi remains in zone 4, but from Delhi to Himalayas there are zone 5 and zone 6. So 3 zones are changing. And if you look at the corresponding value of zone factor, which is given EPGA, now EPGA is related with the return period. So for different return periods, it is given. So we need 73 years, we need 225, 475, 975, and 2475. And even sometimes we can use even higher return periods. So as the return period is increasing, the Z value will go on increasing. So we can compare the current values which are there in our current code, IS 1893 2016, with these values, 2475 years. So zone 5, it is 0.6 proposed, and currently it is, you will say 0.36, I will say 0.54. Why 0.54? Because that needs to be multiplied by 1.5 to convert it into MC. So that is only the median value which needs to be multiplied by 1.5, so that will become 0.54. So in zone 5, previously it was 0.54, now it is 0.6, but this in zone 6, which was also earlier in zone 5. So this is increasing to 0.75. So in place of 0.54, now the bridges will need to be designed for this 0.75. And not only that, earlier we were designing for this value, the 475 years return value, and that was 1.5 into Z by 2. So for zone 5, it will be half of 0.54, so that will be 0.27. So in place of 0.27, now we will need to design it for either zero 0.5 or zero 0.4. Both are much higher. So you can see that now the design forces, especially in bridges, are going to increase tremendously. And the reason for that is, one reason is that the zones have changed and higher intensity shaking has been found to be probable, corresponding to 2475 years return period using PSHA. So the intensity has increased, estimated intensity has increased. Then the return period, corresponding to which we were designing the bridges earlier, that is going to change now. Earlier we were designing the bridges for 475 years, and we were multiplying for important bridges, we were multiplying by an importance factor of 1.5. So you can see that that importance factor still remains more or less same. So it is 0.5 and this is 0.75. So important structures will be designed for 2475 years, but no additional importance factor is needed. So this 0.4 and importance factor 1.5, so that will become 0.6. So this ratio roughly remains 1.5 between 470. Now, coming to the ground motions. This was about response spectrum. We can perform or we can obtain response spectrum either from the code, like we have done that, or we can perform site-specific study also, where we can get site-specific response spectrum. But finally, we have to choose the ground motions. So if we look at the ground motion, different components of the ground motion. So this is same earthquake, but three components, two horizontal and one vertical. So which horizontal components ground motion we are having, along which our instrument is oriented. So any instrument we are putting, actually during earthquake, the ground motion is changing randomly in different direction. So it is not about any fixed direction. The ground motion is in all the directions, and that direction is also changing with time. That's why we get fluctuating or reversible components, varying components in any two orthogonal directions and the vertical direction. And if we know the components in any two orthogonal directions, we can always convert it into any other. We can rotate it in any other direction. So that we can do. What I want you to emphasize on is that please have a look at the peaks. So you can see that these motions are not having peaks at a different time. So both these motions are what we call uncorrelated. So these motions are not correlated. So if these motions were correlated, the peak of H1 and H2 would have been occurring simultaneously. But we can see that these are not occurring simultaneously, and that this is a good relief to us. And same is with vertical. The peak of vertical is also not occurring at the same time when the peak of any of these horizontal is occurring. So these are uncorrelated motion. So when we are using time history, sometimes we use artificial time history. And what people do, if they have to perform biaxial analysis under two ground motions, whatever is given in x direction, they apply in the y direction. That should not be done. So the ground motions are naturally uncorrelated, and the ground motion in H1 should be uncorrelated with H2, and it should be uncorrelated with V, the vertical component of ground motion. Same ground motion is scaled by different factors, cannot be used or should not be used. That will give highly conservative results. Okay, same is true for velocity. So if we look at the velocity records, these are the typical velocity records of the same ground motion, and you can see the same is applicable here also, as well as in displacement. All these parameters are correlated. But if we look at the response spectrum are also different. Okay, but the shape is somewhat similar. So you can see that the shape here and here is somewhat similar, but the values in H1 and H2 of the response spectrum can also be different. So not all the both the components can be equally strong, because there can be some directionality effect. Although the motion is occurring in all the six directions, but in some direction there may be stronger component. The other direction there can be what we call minor component. And the shape of the response spectrum in the vertical direction is very different. It is different than H1 and H2. Currently, our code says that in the vertical direction, we can take the shape of the response spectrum simply 2 by 3, 2 by 3rd of the horizontal. But you can, if you look at this shape of the response spectrum, the vertical direction response spectrum is very different. And it is having higher peak in uh, shorter period. That means in high frequency range, we are getting high frequency. Whereas in horizontal direction, the predominant frequency band is in longer period range or lower, smaller frequency range. Now we can also perform a site-specific design spectrum, and the IRS code as well as IRP code both suggest that when our site is close to a fault, we should go for site-specific response spectrum. So in site-specific response spectrum, what we do, we take into account all the sources. So what you see here, this is a study which we have conducted for this Rishikesh Karnaprayag new railway line. So there are total 16 bridges. Now a few more are also added, but on the original study there were 16 bridges. So these triangles are showing the locations of those. And what you see here, these are the faults. So these lines which you see, these are all faults. And here different magnitude earthquake can be initiated. So we consider all the faults within a distance of 300 kilometers from any site. And we take effect of all those faults on my site. So different past earthquakes which have been recorded in that area, those have been also plotted. And these earthquakes, past earthquake records, these are used to decide the probable uh, magnitude of earthquake or the source potential which is going to occur in these different sources. So each circle here is representing one earthquake. You may be puzzled that how come we are having so many earthquakes. So it is including small earthquakes also. So large earthquakes which make news or which we feel and which cause some devastation, those earthquakes are only few. But small earthquakes keep coming, and those can be recorded with instruments. So if we take the instrumental record, the actual number of recorded earthquakes is very large. But most of those are very low intensity, and those have not caused even those were not even felt by the people. So that's why so many earthquakes you see. So we take into, but those earthquakes are also a good indicator of the magnitude of the earthquake which we are going to have in future at the site. And based on that, we perform PSHA, probabilistic seismic hazard assessment, and this dotted line, this is giving what we call UHS, uniform hazard spectrum. So what is this uniform hazard spectrum? This spectrum is giving equal probability of occurrence. For example, I said 2475 years. So at each period, we take what is the earthquake intensity or spectral acceleration corresponding to 2475 years return period. And what we have to understand is that at different periods, different earthquakes are governing this intensity. So one single source will not give us this shape of the response spectrum. That shape will be different. But here, at different periods, different earthquakes. For example, at longer periods, larger earthquakes which are occurring away from the site, those are going to govern. Whereas in short period, those sources which are nearby to the site, those are going to govern. So different sources are governing different regions of this response spectrum. So this response spectrum is not given by one earthquake, rather it is representing a set of earthquakes, all possible earthquakes, all possible scenarios, which we have identified in the previous slide. And this response spectrum is given for rock site. So if we take at the rock outcrop for the Chandrabhaga bridge, this maximum value, please note, it is 0.6 here. But the same response spectrum, if we, okay, so this is the same, but this is for MC. That one was for dB, this is for MC. So almost double, close to 1.2. And we can also represent these by approximate expressions. So this is the increasing range, this is the acceleration control range, and this is the velocity control. So up to 4 seconds this is given. So this is the velocity controlled. And if we have to calculate Z, so Z rather 1.5 into Z was equal to EPGA, effective peak ground acceleration. So you can see that here the ZPA has been calculated by dividing this EPGA 0.448, which we are getting here. So this is the value at 0 period. If I put t equal to 0, S is equal to 0.448. So this 0.448 divided by 1.5, it comes out to be 0.3. So it is somewhere between zone 4 and zone 5. So same thing has been done on soil surface. And when you consider the soil surface, you can see that amplification. Earlier it was 0.6, now it is close to 0.8. So that much increase has taken place in the peak value. Secondly, you see that the shape has also changed. If you look at the 1 second value, that will make a lot of difference. At 1 second now, it is roughly 0.4. Whereas in the previous case, in 475 years return period, okay, at 1 second here, this is much smaller, less than 0.3 G. Whereas now it has increased to more than 0.4 G. So in the long period range, because of soil, in the long period range, the effect is more. And we can represent this also in terms of similar graph is plotted for 2475 years. And you can see that the amplification here is less as compared to DVE. In DVE, the amplification was more, 0.6 to 0.8. And here the amplification is 1.2, it was slightly below 1.2 to 1.3. So here the amplification is less. And the reason for this is, as I explained earlier, that MC is higher amplitude motion. So higher amplitude motion, the energy dissipation in the soil is more. So amplification in MC is different than the amplification in DV. So this is another important aspect which is currently being missed in our course. And if you consider this in terms of equation and you calculate the Z, now the Z comes out to be 0.34 G in place of 0.3 it was obtained earlier on the rock outcrop. So here does not appear to be much amplification. The reason being that we are considering MC motion, but in DV motion it may be different. So the ratio of DV to MC will vary not only from place to place. This will also depend upon the soil or the site class. In case of rock, the ratio is going to be more. In case of soil, the ratio is going to be less because the DV ground motion will be amplified more than the MC ground motion. So like that, we can plot the UHS. Now, one question which comes to, or which we have to face always, that is whether we should use response spectrum analysis or time history analysis. That question was coming from you in the morning also. So let me tell you, response spectrum analysis is also as accurate as the time history analysis if we get adequate number of modes. So adequate number of modes which are given more than 90% mass participation. Let us say we are getting close to 100, 93, 95. So then the time history analysis is going to give us almost same results as the modal analysis. And just after this talk, Mohit will also show you, he will demonstrate that if you do modal analysis using response spectrum, or you do modal analysis using time history, or you do direct time history, how much difference you get. So the results are going to be very close in both the cases. So response spectrum analysis is also response spectrum analysis using multi-mode method, not the single mode method. Multi-mode method, if you are doing, then the results are quite close to the time history analysis. In case of irregular buildings or buildings where basement and podiums are there, or when we are modeling our bridge along with foundation. For example, I have a bridge with well foundation and you have modeled well also. So in that case, it may not be possible to get 90% mass participation. So if we are not able to get 90% mass participation, then I do not have any other option but to go for, or I have to do approximately the missing mass correction I should do. So whichever, for example, if I am having a bridge with well foundation, and when I will subject it to modal analysis, I will get the mass participation only corresponding to the substructure that is above the well and the superstructure. The well being very rigid, it will not be accepted, and that will move more or less rigidly with the soil. So that's why on the well, I have to consider the forces additional, and those forces I can consider simply m into z. So what I can do, I can make a model of the bridge by fixing the pier at the top of the well, and then the inertia force acting on the well, I can calculate separately, and that I can apply a static force on the well. That's how I can design the well. So that is quite accurate. Or I can perform a time history analysis. If I perform a direct time history analysis, then all the masses, all the modes are inherently considered. Everything gets excited depending on its speed. So if we are considering soil structure interaction, okay, then also we may have to go for time history analysis. And somebody was asking that how we do the directional combination. So this 100 into 30 rule we will use to combine the two horizontal or two horizontal and one vertical component. So because we have seen that the ground motion components, when we were observing them, then the peak in different direction is not occurring simultaneously. And linear time history, when we are performing, it will be performed with minimum 3 sets of ground motions, 3 ground motions, and nonlinear time history will be performed with minimum 11 ground motions. So single ground motion is not adequate. That is another important issue. So this is regarding building. We can interpret this in terms of bridges. So in case of bridges also having seismic devices as dampers, isolators, etc., nonlinear time history analysis may be necessary. So I will say may be necessary. In some cases, the equivalent linear time history analysis or even modal analysis may be good enough. I will explain that more when we will talk about the code on base isolation. In equivalent linear time history analysis, the foundation soil or the device is represented by a linear model, and iteratively, as I explained in the morning, iteratively perform linear analysis, either linear response spectrum analysis or linear time history analysis. We perform iteratively and obtain the solution when it converges. The assumed displacement and the displacement which we are obtaining from the analysis match. Now, the most important question which was there and for which we have done all this background, which you have asked in the morning, how to get the ground, from where we are going to get the ground. So there are 3 sources of the ground motions, 3 types of ground motions are available. The most useful set is which is recorded from the past. So past recorded accelegrams, there are different sites. We are going to give you the details of those websites also, and we will also show you an example how you can download the required ground motions from those websites. So because thousands of earthquakes have been recorded so far and a lot of ground motions are available, which one is suitable to you? That also needs some skillful selection. So you can't just take any random ground motion and start using it. There has to be a criteria that we are going to discuss. But the problem is, even though so many ground motions in the past have been recorded, still those ground motions which match with your conditions, the conditions of your site, and the sources by which that site is getting affected, it will be difficult. So many a times you will not be able to get appropriate recorded accelerogram. That recorded accelerogram may be far away. Okay. So in that case, what we have to do, we will take a recorded accelerogram and we will tweak it, we will modify it slightly, what we call spectral matching. So we will do a spectral matching of that so that it becomes closer. So its natural characteristics will be distorted to some extent, but still some of the natural characteristics will be preserved, and we will use the recorded accelerogram with spectral matching. Then there are simulated accelegrams. Simulated accelegrams are generated using by developing models, computer models of the source and path through finite element or other softwares, and then the ground motions are predicted as response of those models. And then we can have totally artificial accelegrams also, where we can just select randomly some harmonics. We can combine them in a particular fashion so that we get a signal like this, and the response spectrum will match with the target response spectrum. Whatever response spectrum we want to achieve, that can be achieved. And this ground motion is artificial. Normally, this is not used. Earlier, when the recorded accelegrams were not that freely available, then people were going for artificial accelegram. But nowadays, artificial accelegrams are not used. We go for recorded earthquakes in most of the cases. So definitely the real accelegrams have their advantages because these are representing the natural characteristics of ground motion. These are realistic. The artificial accelegrams in many cases can be unrealistic. Then the disadvantage is that these may not be available matching with your requirements. So whatever is your requirement in terms of source characteristics, magnitude, distance, and soil conditions, these may not be available. So in that case, you can select the closest ground motion, which is close to your conditions, and then do a spectral matching or spectrum compatible earthquake you can use. Now, the recorded accelegrams which we get, those may require scaling and spectral matching. So what are the different methods for that? I will discuss a little bit about that. So let's say here, this blue one, the smooth one, this is the target response spectrum, which we might have obtained from code or from site-specific response spectrum, uh, which we have obtained from PSHA. And we get a recorded earthquake, which is close to this, but there is a difference between the two. Exactly matching this response spectrum will not be possible. So what we can do is, the first possibility is that we scale it up. And for scaling, the first point which comes, or the first option which comes to our mind is that let us scale by PGA. So we multiply the ground motion, the whole ground motion, by a constant factor. This is called time domain scaling. In time domain scaling means that I'm not changing its frequency content, I'm not changing its wave profile, but I'm simply multiplying it. I'm simply amplifying or de-amplifying it. I'm multiplying it by a factor which may be more than one, or in sometimes it can be even less than one. You can see that in this case, if I match this spectrum will be somewhere here. But when we have this here, we can see that although PGA is matching, but there is a lot of mismatch in the response spectrum, and mostly our structure will be somewhere here. So that means just matching the PGA is not the correct way. If I match only the PGA, still there can be large difference in the response, which we can see, which we will get from response spectrum analysis and what we will get from time history analysis. Those responses are going to be different because different response spectra we are using. The other way of scaling is that I do not fix the PGA, but I shift the whole response spectrum in such a way that the error between the target response spectrum and the new response spectrum is minimized. So that is the scaling we will use, where in a period range, we need not to do it for the whole period range, in the period range of interest. And what is the period range of interest? Where all the modes of my structure lie, or at least the 90%, the modes which are having 90% mass participation, those modes are lying in that range. And a slight period range beyond that also. So we will consider a period range. the vicinity or at that period, but at other locations, at other periods, you can see that uh, there
Hello,
will
sir.
be. Haman, are you able to hear?
Yes, sir. Sorry to disturb you, sir. Actually, last कुछ time में connection चला गया था, so we
Okay.
couldn't hear what you were explaining in the slide.
Okay, so I will go back to these slides.
Right, right.
This was hard.
Yeah, we heard this one. The next slide was
Next
when we
slide.
lose connection.
So from here I should start.
Right, we did the PGA scaling. After that,
Okay, okay. So I told you that we may not get the required ground motion, which is giving us exactly the same response spectrum, which we are targeting for, which we are looking for. So in that case, what we do, we take the response spectrum or the ground motion, which is having response spectrum closest to our target response spectrum. And there are websites which help us in that. So using those websites, out of those available thousands of ground motions, those ground motions which are having response spectrum closest to our target response spectrum, those will be obtained. So we can select that and then we can do scaling. One way of scaling is PGA scaling, where we match the P ground acceleration with the target P ground acceleration. So in that case, you can see in the response spectrum that all the PGA is matched, but there can be large difference in the response at other periods. So that's why we go for another type of spectral scaling or time domain scaling, in which the error between the target response spectrum and the response spectrum of the selected ground motion is minimized. And when we do it, response spectrum is close in a range, in a larger range of period, we get the response spectrum of the selected or scaled ground motion very close to the target response spectrum. So we use time domain scaling only. We are not changing the frequency content, but we have obtained that scaling factor in such a way that the target response spectrum and the selected ground motion response spectrum are close. Another possibility of scaling is that we scale corresponding to the period of the fundamental. So the fundamental mode, which may be most of the cases, which is the first mode in that direction. In some cases, it may be a different mode also. So fundamental mode is not always T1. In some cases, some other mode may have larger contribution. So that mode, which is having the maximum contribution, we can scale with respect to that. So when we do the scaling like that, it will match at that point, but there may be mismatch at other points. So generally what we do, we take a range around this fundamental period and we match our response spectrum, or we do best fit in that range so that the error within that range is minimized. Although the error in other portion you can see here, this may be more. Here error may be more, but the error here is minimized. So this is a typical example where on the left side you see unscaled uh, response spectra. So some 30 ground motions have been selected, which are returned by the website. So you can see that the response spectra are quite varied. We can scale it with respect to the spectral acceleration at the period of the fundamental period of the structure, which is 1 second here. So corresponding to 1 second, you can see that all the values are matching perfectly because we have scaled it with respect to that. But in this range, you can see the dispersion has increased more, even more than what we were having in the original records. It has increased more than that. So we have to be careful that this type of dispersion should not occur in the frequency range, which can affect the response of our structure. And what is that frequency range? That frequency range is which is causing 90% mass participation in our structure. So you can see that as the modes, we go for higher modes, the period goes on reducing. So higher modes can come up to 90% more. If 90% mass participation we are using, that can come up to here. And you can see that this scaling is not helping, rather it is increasing the error in that. So we have to minimize the error within a range of period. And that range is of interest to us. So if we are not able to do that, we go for what we call frequency domain spectral matching. And when we are doing frequency domain spectral matching, the frequency characteristics of the ground motion are altered. So the ground motion becomes somewhat unnatural. So this we have to keep in mind. So whenever we are doing frequency tweaking or some intervention in the frequency domain, then the natural characteristics of earthquake get lost. But in many cases, our selected response spectrum may be far. Even if we have taken three ground motions, all the three ground motions, the best three ground motions which we are able to get, those may be far away, their shape from the target response spectrum. Even if we are doing time domain scaling, we are not getting very good fit. In that case, we have to go for the frequency domain uh, spectral matching, and number of software are available for that. I will give you a list of those softwares also. Now, recently, this IRC SP114 is getting revised. So this is under revision, and some changes have been suggested or some guidelines have been given for times T analysis. So first, regarding linear times T analysis. So regarding linear times T analysis, this revised SP114 is suggesting that we should have minimum three sets of three component ground motions. So we will consider three components in longitudinal, transverse, and vertical direction, and three such sets we will need. And these ground motions are to be selected in such a way that the envelope of peak responses of the considered ground motions shall be used. Okay, so we will perform analysis for these three ground motions, and we will consider the maximum response of these ground motions. And these ground motions should be preferably recorded ground motions from the available database of past earthquake records. Artificial ground motions should be avoided. And these selected ground motions should be consistent with magnitude, distance, and source mechanism of the site class. So we have to select in such a way that these criteria are matched with the corresponding design response spectrum in horizontal and vertical direction. So spectral matching is allowed, or rather required, to make these spectral match in such a way that in the period range 0.2 TS to 1.5 TL. TS and TL, because any bridge will have different periods in longitudinal and transverse direction. So we will take this fundamental mode in longitudinal direction and fundamental mode in transverse direction. The smaller one of them is TS and the longer one of them is TL. So 0.2 of smaller to 1.5 of the longer. Within that range, we have to scale or spectral match in such a way that the response spectrum, respective response spectrum, will not the design response spectrum at any period. So in this range, after spectral matching, the chosen response spectrum or scaled response spectrum should be above the design response spectrum. It should not be below the design response spectrum. So we will select three such time histories, and when we will perform analysis, we will take the envelope for these three time histories. And here these response spectra are individually spectral matched. So H1 component will be individually spectral matched with the horizontal target spectrum. H2 component will be separately done. And naturally, because we are taking these earthquakes, these records from natural recorded past earthquakes, so these will be uncorrelated. So the risk of correlation is not there. If we were generating artificial time history, then we have to look that both should not be correlated. And we have to perform similar spectral matching for vertical ground motions also, and that will be spectral match with vertical ground motion in the range of 0.2 TV. TV is the vertical period of vibration to 1.5 TV. So in that range, the vertical acceleration will also be matched, and then we will perform analysis of our structure under simultaneously applied three ground motions. So both the horizontal ground motions and the vertical ground motions will be applied simultaneously, and we will consider the peak or envelope response about x-axis, y-axis, and z-axis. that we will use for design. Now, in case of nonlinear time history analysis, 11 sets of response spectrum in such a way that I think again you had the problem. Am I right? You could not hear.
Yes, sir. This
So
slide
I think
only.
this LTHA you have heard.
Right.
You could hear
We couldn't hear NLTH.
NLTHA. So I will talk about NLTHA again. So in case of nonlinear time history analysis, when you are selecting the ground motions, so minimum 11 records are to be selected as per SP 114 guidelines. And these 11 sets will consist of three components: X component, Y component, and Z component, or H1, H2, and V. So H1 and H2 will be scaled together, and these will be scaled in such a way that SRSS of H1 and H2 should not fall below 1.3 times the target response spectrum in this range, 0.2 TS to TL. Why 1.3? You may ask, because earlier we have talked about the target response spectrum. Here we are saying 1.3 because we are doing SRSS. So if you take equal component in X and Y, its SRSS will be root 2 times. So to take that root 2 times into account, this 1.3 is there. So in fact, root 2 is 1.4. So we allow the target or the combined SRSS response spectrum up to 90%, slightly below the response spectrum. Reason is that here we are using recorded accelegrams without any spectral matching. So here we are not doing spectral matching. We are only doing time domain scaling. So time domain scaling should be done in such a way that the SRSS, that is the combined response spectrum of two horizontal components, should not fall below 1.3 times the target response spectrum. The vertical response spectrum, in the similar way, will be scaled separately. It will not be combined. There we will not use SRSS. So vertical will be done separately in such a way that it should not fall below 90%. As I said here also, actually it is 90%. So this is 0.9 into root 2. Root 2 because we are using SRSS of two components. So it should not fall below 90% of the vertical response spectrum, and that in the range 0.2 TeV to 2 TeV. So I think I will stop here, and now we will have some time to take up your questions. So I was seeing some questions were popping, so some questions are there. I will stop sharing now, and Aman, can you take up the questions?
Sure, sir. Mr. Suraj is asking if response spectra of IS 1890 2023, the period of ZPA is 0.01 second. Does it means we can consider the modes up to having frequency 100 Hz for 90% mass participation?
Okay, so you cannot get those high frequencies. Even 33 hertz, the modes up to 33 hertz become very difficult. Okay, and there is debate whether it should be 0.01 or 0.03. So there was discussion in the committee also. Some of the people were saying that it is not possible to analyze the ground motion or to get the response for a ground motion at such a high frequency. And in that case, we can take it up to 33 hertz or beyond 33 hertz. We can take it equal to ZPA or Z. So if you can do it for up to 100 hertz, good, it is better, but that will be difficult. It will be very difficult to obtain modes up to 100 hertz.
Mr. Jay is asking for bridges, at what situations will the vertical ground motion or response spectra be considered for analysis or be critical?
Sorry, your voice was a little less.
Sir, I will repeat the question again.
Yeah, please.
Mr. Jay is asking for bridges, at what situations will the vertical ground motion or response spectrum be considered for analysis or be critical?
Okay. So the answer is that in all the cases. You have to consider the vertical component of the ground motion because earthquake force is acting everywhere. In some cases, it may be critical. In some cases, it may not be critical. That will automatically come out in the analysis. But in general, we should consider the vertical component of ground motions in all the cases. Actually, the same should be done in case of buildings also. So we need not to go into this uh, discussion that where it is critical, where it is not critical. Let us consider it, and wherever it is critical, it will be automatically considered. Wherever it is insignificant, its effect is going to be insignificant.
Okay, sir. Mr. Bush is asking what type of filter we need to require in near fault pulse like ground motion.
What type of filter? So if I have understood the question, I am not clear whether he is talking about the frequency domain filter or a high pass or low pass type of filter, or he is suggesting that while selecting the ground motions, what filter we should have. So currently, our code is not talking about the pulse type motion. That type of motions are not considered here. Uh, and the code says that if the site is very close to the fault, then there is a possibility of such type of ground motions, which can have pulse type of or sorry, velocity, which can have velocity pulse. In that case, we have to do the site specific analysis, and the ground motion selected will be consistent with the probability of pulse motion, which are expected at that site. So wherever there is a possibility in near field of a pulse velocity or a velocity type pulse, we should consider that.
Okay, sir. Mr. Abhishek is asking while doing time history analysis using already recorded data, how the intended lifetime of the structure is accounted for.
Okay, so intended lifetime of the structure we are taking into account in the return period of the earthquakes, which probability of occurrence we are taking. For example, in case of buildings, we are considering, let us say, 10% in 50 years. In case of bridges, we are considering 5% in 50 years. So, sorry, 75 years. So that changes. So the period we are considering in the probability of accidents, 50 years, 75 years, or 100 years, whatever period we want to put that. So that is going to give us a higher target response spectrum. And when we will select the ground motions with the corresponding to higher target response spectrum, we will get higher intensity and probably with higher magnitude and closure distance.
Okay, sir. Mr. Dharmendra is asking for a nonlinear dynamic study like IDA, what will I do if sufficient number of ground motion data are not available at the site? Can I use other ground motion data in case of insufficient ground motion?
Actually, you have to use the best ground motions which are available. So there is no specific limit defined that the ground motion should be within the range. Whatever best consistent with your site and source conditions you can get, use those. So make your best effort through all the available websites. You can obtain from there. And I'm sorry, I have not completed my presentation fully. After this, I have a list of the sites and software which you can use for selecting the ground motions and then processing those. So Aman, today or tomorrow, depending on the time, is going to take a session on that, and there he will cover that.
Okay, sir. Our next question was related to this only. Mr. Sugandha is asking a question. What is the basis of the guidelines for selection of ground motion for different type of analysis?
For different
Type of analysis.
type of analysis. Okay, so this is based on the minimization of the uncertainty. So the variability. If you are selecting ground motions randomly, suppose a bridge is to be analyzed by two people. Ideally, both the people who are analyzing this should come out with the same answer. But what will happen if both people have used different sets of ground motion? Their answers are going to vary. That's the problem. So that's why we need a standardization of the process of selection so that anybody who is analyzing that bridge should come out with the same response. Otherwise, different people can come out with different design. And in one case, it may be safe. Another case, it may be unsafe.
Sir, we'll take last two questions now.
Okay.
Mr. J is asking, we are required to ensure no collapse under MCE. However, under ULS, we are checking for DB. How are we ensuring no collapse under MCE as per Indian standard?
Actually, we are not doing that. Under any code, we are not doing that. The current framework of all our codes, which is force-based design, it can't be done. If we want to ensure no collapse, we have to go for performance-based design. We are not doing, we are not covering performance-based design in this course, but we have been doing courses on performance-based design also, and in future also we will do. There we will cover that how we can ensure a particular level of performance at a particular level of hazard. But in the current framework, it is not possible. So it is just our intention. It is our best wish that if we are designing our structure properly with the code, hopefully it will not collapse under MC level earthquake. But there is no check for that. There is no mechanism for that in the current code-based methodology. And that is not only in case of Indian code. That is true for all codes of the world. Correct.
And the last one, sir, Mr. Tatwik is asking where to find the source data for India and which software is used for PSHA calculation.
Aman will answer this question. There is a software, there is a website called Pasmos. So that is run by our department, and there we are keeping the records of all the ground motions which have been recorded in India. So you have to do a registration to that, and you will have access to all the ground motions which have been recorded in India.
And sir, which software is used for calculation, that will be covered in that session itself. Okay, sir.
This
We'll
comment
close
and
the session here.
recently Mohammed Nawad. If we have a schedule of ground motion, do we need to scale each ground motion separately, or it is okay to scale the mean value of the ground motion? So, if you are considering a large number of ground motions, let's say 20 or 30, it is okay to scale the mean and then take the mean value. But if you are considering only 3 ground motions, then this type of scaling will not work because we have to um, consider the envelope response. And when we are considering envelope response, if mean you have scale, the envelope may be too much conservative as compared to the mean. So it's better to spectrally match individual ground motions or scale individual ground motions.
Okay, sir, we'll stop the session here. Rest of the question we can take in the official writing when we'll provide the self answer for every question or doubts that have been asked.
Okay, so we will have a 10 minutes break.
So, sir,
What time you are starting?
4 we will start again. Mohit will take it.
So at 4 o'clock, Mohit will start. So we still have 10-12 minutes. So we can have a break of 10 minutes. And please do join at 4. We will start at 4. Thank you for being with us. Have a break.